Okay, so let me discuss now the next part of multiple expansion potential as lecture 4b, in which we will consider the after monopole term the dipole moment. Okay, the dipole term, and specifically focus on the dipole moment. Uh, okay, so let's say dipole moment. So this is actually lecture. All right. So we have already seen this in the last summary. This is the summary of the 4A that I had given in that video, in which we had obtained the V of R expanded in some of the in I just noticed in some places in this video, in the last video, some of these terms were um, um, this was missing. This R square was missing. Okay, I hope you have noted that. But here, so this is the monopole term Q by R. This is the dipole term. So in this lecture, I'll worry about this term, okay, the dipole term. In the next video, we'll worry about this term, okay, the quadruple term. All right. Um, so that is, of course, the figure that I have already mentioned our reference. Okay, d tau is the source from the origin r prime. This is from here to here is the r, and the distance between the source and the field coordinate is curly r. All right, just to remind you again what it means. But here everything is written in terms of inside the integral in terms of source coordinates, and outside in red, that is our dominant distance, and that is the field coordinate from the origin. All right. So this 1 by r square, and 1 by r cube are the field coordinates, whereas r prime inside the integral is all source coordinate. The angle between the source coordinate and this coordinate is of course alpha, and it appears here. All right, and that we had already said that we could take it out as a p dot r, and we'll discuss that more. To remind you, this is the I said in the last summary also. Whole effort is to have weighted average of various powers of the distribution with coefficients depending on the orientation, like cos of the field point. Okay, I'm just summarizing the last lecture before I go ahead. The monopole term I've rewritten in here, and we could express it as monopole Q by R. There is a characterization. This is the dipole term. And then we also saw that we could write down simply as P dot R, where P was defined as the dipole moment. Okay, and we'll talk about the quadruple moment in the next monopole, dipole, and this is the quadruple moment. Okay, so this lecture will consider the physical interpretation and uses of the dipole terms. Okay, in briefly. So first thing to note is that in multiple expansion, moving the origin may change the expansion drastically. Okay, so to prove the point, I think suppose I have uh, suppose I have a point charge q, which was initially at q is equal to 0. Of course, there is a monopole, but I keep my origin here, but displace my monopole term in some direction away from the origin, or I take the origin away, okay, by some vector. Does it remain a pure monopole? Okay, that's the question that you ask. Is this a monopole or a dipole now? Okay, Q is still a monopole, of course, but the fact that I have moved the Q from the origin, actually it becomes a dipole, correct? Because from the origin there is a D and there is a net Q. Okay, so not that every dipole is your minus Q plus Q high school dipole. All right. So a point charge at an origin is a pure monopole. We have seen that. But the same point charge displaced from the origin is no longer a pure monopole because of this D vector that has come out. Okay. So it develops a dipole term as well. All right. So suppose we displace the origin, let's say by a vector, a constant vector, let's say A. Okay. So does the dipole remain moment remain the same? That's the question that I've been asking. So let's ask that. And so let's suppose the one p prime, then I would have Ra, it is displaced by A. So let's say Ra prime rho r prime. This is the definition of dipole moment. But now with from the origin to here, let's say Ra. Okay, but I can write down this Ra in terms of the old coordinates, r prime minus a. For example, I've displaced the origin from here to here. All right. So I Ra prime by r prime minus a rho r d tau. Of course, the first term, okay, goes back as p, the original p, okay, rho prime, and minus a, and this is q. So what happens is the new p, the dipole moment, is p minus q and the vector by which I have displaced. Okay, so and hence p prime would become p only when either q is 0 or a is 0. All right, the displacement, there is no displacement. Either there is no net pole. For example, if there is a dipole which has minus q and plus q and the net charge is 0, it doesn't matter where you place it, the origin. It's independent of origin, as I had mentioned even in the last lecture. All right. But once there is a net charge, okay, then the new dipole moment includes the also a QA term. So it is developed. Okay. There is a general claim that, of course, I mentioned that if Q is equal to 0, only then the dipole moment is independent of the origin. There is a stronger claim which you will not prove here, but it is useful to keep in mind that the lowest non-zero multiple moment, this is a slight generalization, the lowest non-zero multiple moment is always independent of origin. In this case, of course, the lowest multiple moment is, of course, the monopole. All right. So the monopole would be independent of origin, which is obvious in any case. But if dipole is the, suppose monopole is not there, if dipole is the only one, okay, as the lowest or the leading order, okay, then that would be independent of origin. This is a claim, okay, which I'll make it, but I will not prove it, but you can take it for granted. Let's look at the electric field of a dipole. After all, that is what we are after. All right. So the so there is a coordinate independent form of the potential that we wrote down, okay, last time itself. That is 1 by 4 pi epsilon naught p dot r. So this does not depend on which coordinate system I'm using. So this is dipole potential is of course 1 by r square, and this is p dot r. Now, once I've gotten this, but there is a convenient way to orient the dipole always. While working on problems also, this to be kept in mind. Okay, that if I especially in spherical polar coordinates, which is the normally the dipole problems are worked in that coordinate system, because the fields of lines are throughout in this with some spherical symmetry. All right. And because of that, there is a convenient way. Suppose and in that case, it is actually simply p cos theta by r square. All right. So, and convenience is there is no phi dependence here. Okay. So to get the electric field, what I should do then? E minus grad V. So I conveniently do this in spherical polar coordinates. While doing this, I have to take some coordinate system. So spherical polar coordinate system is the right coordinate system, and the dipole is actually pretty convenient here. Okay, so let's find out the r component. It's simple, minus del b by del r. Okay, so that's this r square picks up r cube. There's a minus, then become plus. So er is simply 2p cos theta by r cube. Of course, the potential is r square, hence the field goes as r cube. Okay, that's the signature of dipole. Anytime the field goes as r cube, there must be somewhere a dipole. Okay, then the theta is easier to even do that. Okay, it simply picks up minus sine theta, which minus becomes plus. Okay, and then this 1 by r contributes to this r square, and there is a differentiation only with respect to theta, and hence it is 1 by 4 pi epsilon naught p sine theta by r cube. And there is no phi dependence, and of course this will be 0. All right. So we have only the radial dependence ER, which is 2p cos theta by r cube, and the polar dependence, okay, theta, polar angle dependence, that is a p sine theta by r cube. So if you put it together, okay, then of course dipolar theta is p by 4 pi epsilon r cube. P is the magnitude here. The direction is 2 cos theta r, okay, and sine theta theta. This is a formula that I think you will need it so often that even without knowing, you will probably remember on your fingertips, at least during the part of this course. Okay, so this is p by r cube and 2 cos theta r hat coming from here and sine theta theta. There is no phi dependence in any case. All right. If we conveniently put this, have two, for these expressions I have nicely arranged it such that it is pointing in this direction. Only then this theta, okay. So I have only two components. One is the radial component and the other is the theta component. Okay, there is no phi component. That's what I wanted to. So in a spherical polar, that's the most convenient thing to. This, I'll leave it to as a task. You can now convert this back into a coordinate independent form with a cylindrical Cartesian everywhere which you can use. And that's easy to do. So I'll leave it to you. So you can write this out such that it is independent of in which coordinate system you want to use it. So this is 3p dot r hat. Okay. Suppose this is r here, in r hat, 3p dot r hat, and in the direction of r hat, okay, minus the p direction. Now, in this form, you can use it in any coordinate system, okay. This is specifically spherical polar. So this coordinate independent form, all right. So uh, there is a difference between physical and quite often it's not clear. Sometimes you talk about such an ideal that is Q and Q minus are so separated that separated so little that it is indeed a pure dipole. And if there is a distance which you can acknowledge, then it's physical dipole. That's the difference. Okay. So this, of course, we know. Uh, so, and E dipole, I'm just repeating what I derived it in the last slide. Okay, but I have taken it from somewhere. The plot, look at if I plot it is of course a 3D plot because the two Q and Q minus are sitting in space and their fields of lines. So this is a projection, okay. And then you can see the faint blue line here, all right. So that is the equipotential surfaces. Okay, and these are the lines of force starting from positive and ending. Okay, in fact, I had asked you to plot them in the first tutorial itself. I think you were having trouble. Most of the tutors told me that you were having trouble plotting them, but I think it's a good thing to a lot of physical ideas can come by having this picture in mind of how the lines of force behave, even if it is in a projection in some plane. Okay. Um, so this plane especially, okay, you remember this plane? There's a perpendicular bisector plane between, let's say, plus q and minus q. What's happening? That E is perpendicular here. In fact, the potential phi is 0 here. Okay, and there is special significance. So perpendicular bisector plane, no radial component is there. Okay, so there is no radial component, is only the theta component is there here. Okay, and hence in this plane, if you move a charge radially, you pay no cost because v is equal to 0. Okay, so radially you can bring it from infinity even, okay, and wherever you want to place the charge, okay, or another, let's say another dipole, okay, you want to bring another dipole, then you pay no cost in energy, okay, if you travel along this plane. And since it's a conservative, this is an electric field, this is conservative, so anything to be calculated in terms of energy, people choose this, okay, because I can choose, this is conservative. So people choose this plane to travel and then put it, let's say orientation. Suppose there is another dipole which is a different orientation, Okay, then I don't change the orientation, but I first translate it along the perpendicular bisector plane, then I pay no cost. And then wherever I want, then I want to rotate it, then I will be paying only cost of rotating it. Okay, that is how you actually calculated, you calculate the potential or the interaction energy between two dipoles or a charge and a dipole. All right, so that's important thing to keep in mind. Some points to make: the physical dipoles, we have finite d. Whenever we're talking, taking into consideration of our analysis the finite separation between the two charges, this is called a physical dipole. Okay, if you make it so close that I can't, the d is very very small, then I call it a, okay. And remember that by convention, almost p points from negative to positive, the vector. All right, the pure dipole is when d tends to 0, but the q and q tends to infinity, because the dipole moment has to remain finite. Okay, so d tends to 0 and q blows up, but the product qd remains as the dipole moment. Then that is how we call something as a pure dipole. And the what are the constant v surfaces? We have some p cos theta. So and is r square. So if I take all this onto the left side, okay, or in this, and take r square here and bring the dipole potential for constant potential here. So if there is a constant, then I can see that r square is equal to c cos theta. So these lines, these faint blue lines, are r square is equal to c cos theta plotted through a computer plot. All right, you can also plot it. You have learned how to do this in polar coordinates. Okay, but this is only in one plane. Then what do? Then I rotate it around to get the surface constant, the equipotential surface, okay, around the symmetry element in phi, to get the whole equipotential surfaces. But it is important to remember that r square c cos theta gives you the polar contour line, which has to be rotated around the symmetry axis to obtain the equipotential surface. So how do I, suppose I ask you to find out the divergence of the field due to the dipole. Okay, please try that. Okay, and tell me what do you conclude. All right, so we can discuss that. So divergence of the dipole. Okay, this is now straightforward. You have the expression. You know how to take divergence in spherical coordinates. You can calculate. All right. All right. The other thing that we are interested in is what happens to dipole under external field. Okay. Of course, it can experience a force and a torque. If the net uh, is zero, net like let's say minus q plus q, then it will only experience a torque. Just I said, you could actually travel. All right, this can be proved itself. See, Griffiths uses for torque a very unusual definition. If you have come from a mechanics where we are normally normal force, but this is because he has used up tau to use volume, and that's why he used capital N is a torque throughout the text in this course. So I'll also follow that. It's very unusual, but we will follow Griffiths in its notation, so that the textbook notation and our notation match. So of course, this is straightforward. This is d by 2 and q. So QE is the force, and if my origin is this, then this is the torque. Okay, and for minus d by 2 from this origin is minus q by e, so it adds up. So this becomes d by 2, d by 2 becomes qd, and hence the torque is simply P cross E. Okay, is an important formula, that very convenient formula. The torque due to of a dipole in presence of an external field E is simply P cross E. Okay, and of course here there is no net force. This force and this force are equal because Q is the same. Suppose Q is not the same, or E is not the same everywhere. Here I am assuming that E is uniform. Okay, so that's why the force here and force here is, balance out. But suppose here force is more, then of course it will try to the here I'll have a net force. All right, so how do you calculate that? So the two forces may not balance, so you calculate by Fx. Okay, so this is delta Ex dx by delta x. How much does the field change in terms of delta x? Okay, delta x changes in delta y. In three dimensions, delta x, Ex can change. Okay, in Ex can change in the x direction, Ex can change in the y direction, Ex can change the z direction. So you just take that and multiply by that q. Okay, and this is nothing but q into delta x. Okay, you can express it as px. You can actually the displacement that we have over d, you can always resolve it like any other vector, p cos theta, p sin theta. So q into, so delta x over the separation between the two from the origin or the 2 points, that becomes px, py, and pz. So the x component of the force, okay, has three terms, okay, coming from, so this is only ex. So that is why it's fx component, okay. But ex component can change in x and y and z direction, and that will interact with p's, px, py, and pz. And that is how we write fx component is p dot grad of ex. Ex is like a scalar component of E. So I'm taking that grad and then dotted with P, and that is this quantity. Okay. So I have to do similarly for Fy and Fz. Then only I'll get, okay. So and hence I can write down that is P dot divergence of the Ex component, treating Ex like a scalar. Okay, divergence, sorry, gradient of Ex. Okay, so this is gradient of Ex, I, so gradient of Ey, J, and dotted with gradient of E delta Zk. And that is why this expression is for the net force, P dot del or nabla, okay, P dot nabla, working on each of the components of E. So this is in fact right in the first discussion hour somebody asked this, and I had said how it works out. All right. All right. So let's take the example, so that the energy of an ideal dipole P in E is U, that is the interaction energy, minus P dot E, and hence obtain force on it. I described to you force because of the non-uniformity of the field, but you could also first find out the interaction energy and then obtain, of course, force minus of grad U. Okay, so that also one could do. So so let's calculate the energy. It's very simple. So U should be Q V at whichever point it is there in R. Okay, so force on a physical dipole is minus Q at R and plus Q at R prime. Okay, so and hence I can calculate, okay, the over the D, for example, what is it? Okay, so QV R plus D and minus Q VR, okay, the potential difference. And this is nothing but as if E dot dl, okay, from R to R plus D minus Q, right? Straightforward, okay. But this is for a physical dipole. But I'm saying that for a pure dipole, this D is almost negligible, okay. So in that case, I can approximate this because D is going to be almost negligible as a QE dot D. And in that case, for an ideal dipole, as I mentioned it here, so this is, so Q and D gives you minus of course the Q into D vector gives me the dipole moment vector in dot E. So that is the interaction energy. Okay. So this thing I'm reducing it to E dot D. That is the only thing that I'm really doing. So because D is assumed small, and now you can prove, of course, I can get F is equal to now from here. Okay, but here you can see this is grad of P dot E. That is the energy. Okay, so minus minus is of course giving this is force is minus of grad, but there is an interaction energy itself that is minus, and so it is simply grad of P dot E. Okay, and I had obtained the so as a home task, you can show that in the last slide I said that force is this, sorry, this. Okay, and here I'm saying is this. Please make sure that the two are actually the same. But most often we use this as the most convenient expression. Okay, so to prove this, the hint is that use product rule 4 in your book cover, and just expand this and see which terms are zero, and you will get this. All right. So you, but in practice, in terms of problems, you could either use this or this. Mostly this is convenient when E is given directly. All right. Now let me, before taking up any other problem, what are the significance of dipoles? I cannot overemphasize the significance of dipoles. They're just everywhere. Okay. Because you remember we said that most of the bodies that we deal with, whether it's in astronomy or in everyday, they have lots of charges, but they're balanced out. Okay. So everywhere, since most bodies are neutral, so most of the times the electrical interaction is really because of dipoles. Okay, so most molecules either develop induced dipoles. Okay, you have read, probably have been calculated this dipole moment in your courses in chemistry. Okay, so all these are polar molecules. So let's say water. Okay, water I've given example here, but and they're typically there. The dipole moment is a very small quantity. Okay, in most cases for molecules, and hence it is measured in terms of 1 dBi, and dBi is 6.1 minus 10 to the minus 30 charge, of course, in distance, c coulomb meter. Okay, so this is for the water molecule. This is about 108 degree. Okay, so oxygen and water, and that pH2 is 1.8 dBi. All right. So similarly, one can give the configuration and ask for what is the dipole moment of any of these and how they're oriented, like NH3. NH3 is a three-dimensional structure. This is almost like a planar structure. Most of chemists' organic solvents are polar. Okay. Then neutral atoms interact via dipole-dipole interaction, okay, leading to van der Waals forces. That is how actually most of the interactions occur. For example, in your mechanics course, you might have come across this term is Leonard-Jones potential. There's potential energy. There's one atom, neutral atom, let's say, is at the origin, and another distance with another. Okay. Of course, if they're very far off, they are no interaction, and they are two like separate atoms. But once another neutral atom starts coming, then they start interacting each other, and each one another, they induce dipole moment on each other. Okay, and so this is induced dipole moment. Okay, the one each other inducing dipole on each other, and hence the interaction is 1 by RQ, and 1 by RQ goes as 1 by R6 and is attractive. Okay, but when the two atoms come very close, then there is an overlap of their electronic cloud. They are basically neutral, but the electronic clouds don't like overlap. Why? Because they are Fermi. Okay, they don't like to. So there is a huge repulsive between electron. This is not electrostatic. This is quantum mechanical because they are spin half. Okay, so and that gives rise to this R to the power 12. Okay, and this is repulsive. This is positive. Okay, so in a very short distance, they are repulsive, and in very long distance, they are attractive. Okay, and because of that, these two can have a minima, and and it's minus, so a dipole can get actually stabilized here. Okay, and around it, dipoles normally oscillate. Okay, with temperature. Okay, so even this is an important mental model for even for solids for the neighboring atoms. Okay, so and to my biologists or chemist friends outside, life would not be simply possible. They're just everywhere. Dipole interaction, just protein folding, the way our tissues get made, the way we get made. Okay, it's happens because of how the proteins fold as a functional difference. Protein folding is completely controlled by dipolar interaction. Okay, for example, the hemoglobin carrying oxygen, okay, involves dipolar interaction. If the dipolar is somehow prevented, then your life will not be possible. Okay, because the hemoglobin would not be carrying oxygen to different parts of the body. Okay, uh, and of course oscillating dipoles. Okay, in your mobile you have a dipole which is oscillating, and that is how it is communicating with the dipole that is on the tower. Okay, but these are, for example, all the hanger can be used as a dipole. Sometimes you might have used in the early days when there used to be transmission of the TV lines. Okay, or you have seen the TV transmitters. They can simply be rods of many. Those rods are nothing but dipoles, but they're oscillating dipoles because oscillating dipoles radiate. Okay, so all your antenna for communication are time varying dipoles. Okay, in fact, soon every object will carry a dipole for IoT in the new 5G world. All right. So, and because in the 5G, actually interaction will become these driverless cars. Okay, so every object will every car would have, so that one driverless car would know where is the other car or other object. Okay, maybe we'll all carry a 5G antenna on our body. In fact, every Apple might have a 5G antenna. That is what is Internet of Things is going to do when the internet becomes even faster, such that machines can take feedback and there is no time lag between sensing and acting. All right. So dipole is and in your electrical engineering courses, you will be a fundamentally Hertzian dipole. You will be doing it in a lot more detail. Okay. So with that, we can take more examples of home assignment later. Okay. So we have come. There are a couple of problems I'll give both in practice problems and home assignment and dipoles. But next we will really go to quadruple moment and do some problems there. That is new, so we'll do some more problem there.